Hey there, this is Arnav from Pebble, and welcome back to the Introduction to Linear Algebra series. In this video, I wanted to talk about solving linear systems and Gaussian elimination. In the last video, we went over row-reduced form and also the basics of writing a system of linear equations as both a matrix equation and an augmented matrix. And I want to build on that and actually show you how you can use matrix methods to solve a system in a fast and efficient way. So first off, let's understand the traditional approach to solving a system of linear equations. Normally, you would manipulate the equations in some way so that the resulting equations are something that you could solve pretty easily and have the same solutions as the original equations. And the way you would normally do that there's three ways. So you can swap the positions of any two equations. You can multiply an equation by some scalar, and a scalar that's non-zero. And you can also add to one equation a scalar times another equation. And we can also do the same thing with an augmented matrix, and we're going to call these elementary row operations. So since we note that each row in an augmented matrix corresponds to a linear equation, we can just restate these in those terms. So our first one would be to interchange any two matrices, any two rows in the matrix. So I'll write that here. So we're going to say R1 is going to equal to interchange any two rows of the matrix. R2 is going to equal multiplying any row by a non-zero scalar, and R3 is going to equal adding to one row a scalar times another row. Okay, so these are what we're going to call elementary row operations. Elementary row operations. Beautiful. Okay. Looks good. And so with this knowledge, we can now go into the technique we call Gaussian elimination. And this is a multi-step matrix method that uses these three elementary row operations for solving simultaneous linear systems. So what are the steps that we have to do? Well, let me take a linear system. So let me just write one out real quick. So we're going to say 2x plus 3y plus z equals 16. And then maybe we can also say something else like, actually I'm gonna make this 2 variable just for simplicity. But yeah, so 8, and then we're gonna say something like 3x plus 2y, and we're gonna say that's equal to 10 or something, right? So let's first do step 1, which is constructing our augmented matrix. Okay, so the augmented matrix, as we covered in the previous episode, would look something like 2, 3, 3, 2, 8, 10. And remember, an augmented matrix is that combination of two matrices separated by a partition. And so this is our augmented matrix for this particular problem. And step 2 of Gaussian elimination is to use these elementary row operations that we just covered to transform the augmented matrix into row-reduced form. And that'll give us new equations that are simple to solve, right? So we need to get rid of this 3 here, basically, for row-reduced form, because we've learned that we've learned that everything under this 2 needs to become a 0 in row reduced form. So what scalar or what row operation can we use? I'm going to give you a moment to think about it, and then I'll go into it myself. Okay, so hopefully you've had an opportunity to think about that. And what I would do here is I would take the first row, and so we're going to actually be using operation number 3 here. I would take the first row and then multiply it by -3/2 and add it to the second row. Okay, so that would look something like, let's denote these as lowercase r1 and lowercase r2 for the rows. So r2 minus 3/2 into row 1. Okay, and that's going to give us, well, that would be -3/2 and then yeah, so that'll give us 2, 3, 8, and then 0, 5/2, and then -2. And you obviously will do this to each value in the first row, multiply by -3/2, and then 3/2, and then add it to the next one. That's why we get this here. Okay, so that's great. So this is a lot easier to solve because now we actually know that now we only have one coefficient for whatever y will be. So now we have the augmented matrix. We're going to turn this back into an actual system. So 2x plus 3y equals 8. That stayed the same because we didn't do any operations to it. We didn't need to. And then we would get 0x minus 5/2y equals -2. Okay. And now we can actually, now as you can see, we just simply solve for y here. So y would be, it would be 4/5 here. So 4/5, and that's y. And now we can just substitute this into the first equation, and we should be getting 14/5. So that was a very, very basic example of how we can solve something using Gaussian elimination. But I hope you can imagine as you get more and more equations, because you can use, I don't know, 3 or 4 equations here, and everything would sort of make sense, right? And you can also have 3 or 4 variables, and if you do the same thing just using your row operations going one row at a time, then this becomes significantly easier to actually solve, because at a point you will get hopefully you'll just get one variable, and that one variable will just, and that one variable will be all you need to solve this equation actually. Okay, so let's actually just take a look at a more complicated example. I'll do one with 3 variables and 3 equations just to demonstrate what I'm talking about once again, and also give you a better sense for using these row operations because they are very, very important in actually solving linear systems, as you can see. Okay, so here's a problem that I think will be pretty fun to solve together. And before we do that, obviously, please do pause the video, try it for yourselves, and then we'll go on to it in a couple seconds. Okay, so hopefully you've had a chance to take a look at the problem on your own and try and get the answer on your own as well. So let's look at what we have to do here. So the first row it can be left as is, I think. And then the second row, we obviously need to get rid of this 3. So we're going to do the same thing that we did up there. We're going to multiply by -3/2 of the first row to these, and we're going to add that to the second row. Okay, so I'm just going to denote this like that. So -3/2. right? And hopefully that notation makes sense. And what we're gonna do then is just actually do this real quick. So that'll give us, keep the first row the same, 252 minus 38. And then the second row will become 0, and then that should become minus 19 by 2. 1, and then 74. And then the row stays the same. So 6, 1 minus 7 minus 12. Okay, so that's step 1. Now, on a step 2, first gotta get rid of the 0 here, I mean the minus 6 here, and then in the next step we can get rid of this 1, or whatever that 1 turns into. So for this one, we're just gonna add, we're just gonna subtract this minus 6 using this 2 here. So this will be, I guess, minus 3. And then we're just going to subtract that from there. So that'll give us, first row stays the same, minus 38. And then second row will also stay the same. So minus 19 by 2, 174. And then the third row, it's going to become 0, and then this should turn into a 16. And then this will turn into a minus 1, and then the final one will turn into minus 126. Right, partition back in, and that looks good. Okay, so now we gotta do a little bit of a annoying piece, which is getting rid of the 16 using this minus 19 by 2. And to do that, we need to multiply by 32 by 19. Multiply that row and then add it there. I mean, subtract it there, I think. Actually, we'll do minus 32, and then we're just gonna subtract it. Okay? Or you could add it, but I'm just gonna do subtracting because it feels a lot more natural to me. And so that'll give us 252. First row stays the same. Second row will stay the same. Into 174. Third row will now become 2 zeros in the first 2 columns. And then the third will become 13 by 19. And then the final column will be minus 26 by 19. So partition is made. And now you have basically the value of z, because now it's just 13 by 9. 13 by 19 equals minus 26 by 19. So let's do that real quick. 13 by 19, z equals minus 26 by 19. That looks pretty self-explanatory. 7 equals, I mean, z, I don't know where I got 7. Z equals minus 2. And then now with that minus 2, we can just plug that into our solution for y. So minus 19 by 2, like we have up here. Y, that's just going to equal 74. I rearranged the equation here. Minus z. So that's going to be minus 2. And then that's just going to equal 76. So dividing, canceling this out, that's just going to give us minus 8, I believe. So y equals minus 8. And then we're going to plug all of that into our equation for x. So 2x equals minus 38 minus 5 times minus 8 minus 2 times minus 2, which is just going to give us 6, and x will equal 3 in that case. So the solution that we've got here is that x equals 3, y equals minus 8, and z equals minus 2. And that was pretty simple to do, coming from an equation that had 3 variables, 3 equations, and there's really no fun way to do this one, except for using matrices. And this is pretty simple. It was really only a couple of steps. And all you gotta really do is think about the factor that you have to multiply by, and then if you're subtracting, you're adding, and that'll just get rid of the row, that'll just get rid of the value for you. And from there, it's pretty much just smooth sailing, and it's really, really efficient to work this way. And so Gaussian elimination is of that type. It's a pretty important method to know how to do quickly and efficiently. And so some of the time you won't get these perfect, like, upper triangular matrices. Sometimes this will just turn out to be 0, and that just means that you're gonna have I guess more solutions, and C can be 0 in that case, which it just makes stuff easier for you because you only really have to worry about x and y. And so yeah, there's one theorem that we do need to go over, but I did mention it briefly in the previous video, and that just means that if you have more variables in your system than you do equations, so if we were to take out this last equation, then this would basically just have infinitely many solutions because you have 3 variables and only 2 equations. So there's multiple ways you could define any of the 3 variables to get the same equation, and that just so happens to be infinite. And I'm sure there's a proof online, but we won't go on into that right here because I guess that's a bit out of the scope of this video. But yeah, that pretty much completes Gaussian elimination for you. And in the next video, I'm hoping we can move on to determinants and hopefully a bit of the inverse. And yeah, I'll see you in the next video.